下个礼拜会。
可能会被延迟。
要
什么？
对，
因为来不及。来不及。啊？什么？OK。别的科呢？别的科。
或者是另外。OK。
要不要延一个礼拜，还是直接把最后一个合在一起做？
哦，就变成4个配套
啊？
变成4个配套。
没有，就变成4个 quiz 的话，就说少一个。如果合在一起，就还是有一个。
哦，这个
合在一起的。啊？
分开算。好。
就算成呀，就照算哦，照算。怎样？不然的话就要连着考，没有时间了。我不想在最后一个礼拜考，不能讨论。如果在最后一个礼拜考， Seng. Is Eric Kun here? Eric Kun. Eric Kun. Who's Eric's friend? Is anyone Eric's friend? Eric. Oh, Eric. Otherwise, no one. I don't know. Hello? Okay, I think we should start. Good morning to everyone. Today we will review the exam paper in the tutorial time. And for next week quiz, I think we probably need to postpone, maybe. If postpone, you guys want to like do joint quiz at one go, or you want to do one by one, because there's not much time left already. If I don't want to do quiz at the last week, Eric, okay, finally. So I mean, we can either do quiz the next after we have the following next week, and then 2 weeks after, or we can do a joint quiz. So we combine quiz 4 and quiz 5. Combine. Okay. Okay. We will consider. Okay. Okay. Today we'll start the lecture. So the lecture. Okay, the lecture today. Okay. Last week we talked about the locality on the path on the graph. So we look at the neighborhood of vertex. Okay, you stand on the vertex and then look at your neighborhood. So who are connected to you, and then we have some simple operation. Look at the subgraph, taking union, checking what how is the graph bipartite. Okay. So today we will try to walk on the graph. Okay. So today you stand on the vertex and then you try walk following the graph and then see what property we got from the. Okay. So first we will define the path. A path on the graph. So let's start with an undirected graph again. So a path of length n from one vertex u to the other vertex v is a sequence of edges. So if it is length n, then you got n edges. If you got n edges, then you got length n. Okay. Such that EI has endpoint SI and SI plus 1. Okay. So you need example or not? Yes. Okay. So again, so for example, you got this graph here, right? Okay, and then you label your graph as use x1, x1, then x2. Okay. Okay. So here I think I need to add something such as x1. So your starting point is u1, and the ending point is, so here is the u, here is the v. Okay. Then side u1. So your sequence of path is a path from u to v is e1. Okay. But when your graph is simple, you can just use endpoint to denote, because there's no ambiguity of what path you're taking. Okay, so let me write it down. So when your graph is simple, you can denote the path by vertex. Okay, because you don't have the ambiguity that that which path you are taking if you are going from E to S3 to S4. Okay, so about that. So you can just use vertex to describe if your path is if your graph is simple. Okay, and then next one is the path that start and end at the same place. So this path we will call it a circuit. So a loop is a circuit, but circuit is not a loop. Okay. Because loop we define as the zero, the path zero, is it path zero? Length one path, oh yeah, length one path at the vertex. Okay. Length one path at the vertex. But circuit could be longer. Okay. So circuit has length more than the zero. Okay. So circuit. So for example, the circuit can be like this. Okay. So let me add these things. So circuit is so E1, E2, E3, E4, E5, E6 is a circuit. Okay. So you go like this. So go circuit, go path. Okay, and then some terminology. Later we will use them a lot in various ways. So as you would know, a length of path of zero length is just a vertex. Okay, so you are not walking, so you stay on the vertex. So sometimes we will call the path a walk. Okay, you see walk, it's also a path. And a circuit is a closed walk. So you walk back to your original point. And then the next one is the simple path. So what's a simple path? We know simple graph, right? Simple graph doesn't have loops. Doesn't have loops and multiple edges. Okay. So what's a simple path? Simple path also we call trail. Okay, is the path with without multiple edges. Okay, so you don't have something like going E1, E2, E3. Yes. So for this case, E1, E2, E3, not simple. Okay, so no multiple edges. Okay, so what we just discussed is the undirected graph. So try work out the directed version. I work out this definition. For directed. One thing I can tell you that is, so if the direction is not the same, you cannot compose them. Okay? You only can compose same direction. So you can go from here to here, but not from this way. Okay? So you can only compose same direction if you got direction. This one like okay. But okay. So you cannot compose this way or this way. You can only compose with the same direction if direction is this. Okay, so far okay. Today I'm going quite fast because there's quite a lot. And I think it's quite new and then you need to think about it a bit. So maybe we'll think a bit. Okay. Okay, so far. Okay. Okay, continue. Okay. Next thing is about connection. So when do we call a graph connected? So how connected you want it to be? So when you say a graph is connected, if for every 2 points, there is a path. Okay. So you can reach every 2 vertexes through the edges. Then this graph is connected. Okay. If it is not connected, then we will say disconnected. Okay. Okay. For example, this triangle C through right cycle is connected because every 2 points you can find a path between them. Okay. But something like this is not connected. because you cannot reach these 2 points here. For example, let me call it A. So you cannot reach, you cannot go from A to C, you cannot go from A to B or A to similarly for B. Okay? So these are disconnected. So it's disconnected. So how do we call these pieces? Okay. So these pieces we will call them connected components. Okay. So there are 2 connected components. And then here is 1 connected. So how to make this precise? So the definition of connected component is the connected component of a graph G. First of all, is a connected subgraph of G. That is not the proper subgraph of another connected subgraph of G. Okay, note that this second sentence very important, right? Okay. Otherwise, you will say that CD is a connected component. Okay. But it can't be a proper subgraph of another connected subgraph. So this one is a proper subgraph of a connected subgraph. So we don't want to consider consent. We don't want to consider further into this subgraph. Okay, we want just to look at the largest connected piece. Okay, make sense? Make sense? Okay. So this definition is to make sense, to match your intuition. Okay. So for example, in this case here, this graph is not connected, right? Because you cannot connect D to B or D to C or D to H, D to F, or similarly for you. Okay. And then there are 3 connected components here. Okay, make sense? Make sense? So far, okay. Okay, so there are 3 connected components here. Okay. Okay. Okay, so go to the next one. So next, this old time, this mayor of this town for the Königsberg. So there's a 7 bridges connected to the town. So they ask whether there's a circuit that can pass through every bridges exactly once. Okay. So you can try and think whether you got a circuit that can pass through these bridges exactly once. You can try and draw. No. Why? How you know? Test algorithm. Oh, you guys did algorithm on this thing. Oh, okay. Which course? Oh, why you guys did this algorithm? Under what subject? Searching. Okay. I'm not sure there is the algorithm in the textbook. Is it the same or not? You can go and see. Okay. Okay, good. Then let's introduce the solution. Okay. Testing. Okay. So what's this question asking here is actually what we call the Euler path. Because this question is solved by Euler, so we call it Euler or Euler circuit. Okay, so what's an Euler circuit? So an Euler circuit in a graph G is a simple circuit containing every edges of G exactly once. Okay, and then an Euler path. Similarly, you can form an Euler path. So just that Euler path, no need to require the starting point and the end point must be the same. Just use this. Okay. So let me copy the example first. Okay. Try 2 minutes. You see if you can draw Euler circuit or Euler path on this graph. Directed and undirected. Draw a circuit or path that passes every edges exactly once. Try and draw. See if you can find. Try and draw. Can discuss with your friend. Any idea? Anyone try out? Anyone found some Euler circuit or not? G1 has an Euler circuit. Huh? So you can start from A. Yeah. So which way you want to go? B, E, huh? D, D, and then E. Huh?
So each the vertex will pass along.
Yes, vertex, no restriction of vertex. We will have restriction of vertex on the Hamilton path. Okay. Euler path, only restriction on edge. Okay. How about G? G has no Euler circuit. Okay. You can try it out. But you wrote an algorithm. Okay.
Just draw it out.
That's very yeah. You need to test. I mean, you need to argue. How about G3? Path or circuit? Path. Okay, so you can find a path. So start from A. Where you want to try? D. Okay, only one way to go. D, then E, then E, then E. Then one way to go A. Then okay, yeah. Can How about figure 4 H1? H1, you see this one cannot match. Okay, because the direction not the same. Unless you can go back. Okay, otherwise this one no. Okay. How about H2? H2 you can find on the circuit, huh? Which one you want to start? You can start anywhere. I think so. Start in. Yeah, let's try walk around this path. There's only one way to walk. Okay. Euler circuit. H3 Euler path. So try. I think just only one way to walk around this thing because the direction restrict you a lot. Okay. Euler path. Agree? Only one side each each edge. Okay. So in general, how to find this Euler circuit? In general, how to find Euler circuit? Give you a large graph. So there's a theorem where you can just count the degree of vertex. So let's say you start with a connected multigraph. So you allow multiple edges with at least 2 vertex. You need to at least 2 vertex, right? 1 vertex you cannot form the. If you put a loop cannot. Put a loop can. So as an Euler circuit, if each of is a if and only if each of its vertexes has even degree. Okay. So there are 2 directions. If your multigraph has an Euler circuit, then your vertex have even degree. If every vertex has even degree for your connected multigraph, then you can build a Euler circuit. Okay. So let's see how this argument go. So one direction is easier. So if you're going forward, it's easier. So you got a Euler circuit, then each vertex has the even degree. Okay. So instead of writing down, maybe I just draw the diagram while explaining. So suppose you got an Euler circuit, right? Okay. So this Euler circuit, maybe you start with A. Okay, maybe I do step by step, otherwise start with A, right? So you start from A, then your degree here is +1, right? Okay, because you've got one arrow coming on. And then you keep moving. While you're moving, each time you pass a vertex, it's +2 degrees to the vertex. Because you need to go in and then go up. Okay, automatically you will add 2 to the vertex. Okay. That it doesn't matter if this this path here pass through A again. Okay. It will add an even distribution again. Okay, right. Makes sense. Huh? What? Okay, when you pass, even though if you pass through A, you still add a +2 contribution to the degree of A because you need to go in and then go up. Okay. So in the end, this is a circuit, right? So you need to turn back to A. Yeah. So you got another +1. So you get a +1 from going up, and then you get a +1 from going in. And then each time you pass through a vertex, you contribute 2. So everything is even. Make sense or not? Make sense? Make sense? No? Why? Which part? Which part don't make sense? So okay, let's say Okay, let me repeat again and then see which part doesn't make sense. Okay. So let's say the circuit start at vertex A, okay, and ends, of course, they need to end at the same place. So when you start here, okay, you got a +1 degree to the edges because you got one coming up from A. And then each time you pass through a vertex, you get a +2 to the vertex because you go in +1, go out +1. So it's 2. So every time you pass through one vertex is 2. Okay. Uh, Euler circuit allow you to pass through A again. Okay. Maybe in the middle of the path you pass through A again, but this is +2, right? Because you go in to A, go out from A. And then you maybe go somewhere else, and then you come back to A again. Because this is a circuit, you have to come back to A. So this going in +1 to the A. So +1 at the start, +1 at the end, so it's +2. Okay. So that's the okay. So in the so in short, every vertex got a +2 contribution from the path. Okay. So everything is equal. Make sense? Make sense? Make sense? Okay. Following? Okay. Okay. So yeah. So that's mean if you go to Euler circuit, every vertex has even degree. How about the other direction? The other direction is harder. Okay. So the other direction can split into few procedure. So one is you have to show that you can always form an Euler circuit using even uh, degree of even degree of even degree of vertexes. Okay. So whenever you got even degree of vertexes, you can form an Euler vertex. Okay, maybe for example, let me show you some examples. So let me show you one example. So okay, so now you start with an even degree vertex. You want to build an Euler circuit. So let's say, for example, this one just example. So what Euler circuit you can form? Maybe you can form something like this. Okay? Or maybe you can form a shorter one. So something like maybe. Okay. This one also Euler circuit. I mean, Euler circuit correspond to these four vertex here because you uses up four of these. Okay. So so that's mean in general, either you can form the how to say the total one in general you might not find the can I use total Euler circuit? Do you understand? Like okay, in general you might found the Euler circuit or you might found a smaller Euler circuit correspond to the subgraph. Yeah, subgraph of the graph. Okay. So in this case, right, even if you get the purple one, that's fine because you can consider the subgraph that removing that part. Okay. So what do I mean by that? So you can like split off these two. Okay. So let's say you found a smaller Euler circuit correspond to the subgraph. Okay, proper subgraph. Then you should ask yourself that whether you can found another Euler circuit for the other part of the subgraph. Okay. If you can do it, because this one is connected, right? So you can connect these two Euler circuit back. Okay. And then all together you can get the total, the green, the whole Euler circuit. Okay. Is it like okay confusing or not? Understand? Understand? Not really. Okay. So okay, I repeat again. So okay, so next part, the second part is you start with even degree of vertex, and then you want to show that you got an Euler circuit. Okay. So if you got, you need to show that you can always form an Euler circuit using even degree of vertex. Okay, this one is done in the textbook. But the concern here is, even if you found the Euler circuit, that Euler circuit is maybe sometimes just correspond to the subgraph. Okay? Sometimes just correspond to the subgraph, because this is also Euler circuit, right? Because it passes through the edges exactly once and then come back to the original point. But in this case, in the purple case here, you didn't pass through the rest of the vertex. Okay. So what you can do is you can consider the subgraph removing this part. Okay, then you look at the rest. The second connected part. Any question? No? Maybe you ask question. Which part is not following? How to get the purple one? The below. Huh? How to get the subgraph? Huh? Okay. So let's say okay, let me write. Okay. Okay. So for example, let's say you start with this vertex A, right? And then you try to walk along the graph. You try to walk along the graph. And then you think that, hey, I'm done. Euler circuit. Yay. Okay. But you found that actually you haven't passed through these 2 points. I mean, haven't passed through these 3 X here. Okay. So what can you do? What you can do is you consider the subgraph which remove this small Euler circuit. Okay. So you look at this, the edges that you haven't passed through. Okay. And then you realize that you also can form a Euler circuit, because when you take away this subgraph, this subgraph here, the triangle subgraph here still satisfy the condition that the vertex is even degree. Okay. So you can form another Euler circuit. Okay. And then after you form the Euler circuit, you can combine these 2 Euler circuit because they are connected. Okay. Then once you combine these 2 Euler circuit, then this is the circuit that you want. Okay. Makes sense.
Right.
What?
Take a look.
What do you mean?
Divide it and take a look.
Yeah. So it's like you do it, how to say, part by part. Yeah. Okay. Yeah. Okay. Okay, maybe I just show you one example. Yeah. I show you one example. For example, this guy here. Okay. So the clamp is this has a Euler circuit. This has an Euler circuit. Can you draw it in one how to say? Can you draw the Euler circuit without lifting your pen? Yeah. So one way to solve this, right, is they draw two Euler circuit. Okay. So one is like this, 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 this. Okay. And then the other one is the symmetry one. So you start from here, and then go around here, and go up. Okay. So this is called the Mohammed Shimatas. Okay. Why Shimatas? Shimatas is the like the sword. Okay. You can see like the sword. Okay. So it's like make up of two swords. Okay. So once you got these two Euler circuit, right, and they are connected, let me so connected here and then here, right? Okay. So through this connection, you can form the the Euler circuit of this one. Okay. Is that okay? Yeah. Yeah. So the key point here is this graph is connected. So you can like split the part by part up. Since they are connected, then you can connect the path back. So you can like join different Euler circuit together. Okay, so the key point is the connected part, connected of the multi-graph. The connect, yeah. Okay, so where's the bridge? Okay, so maybe we come back to the bridge question again. So we got a town, okay, and then we got a bridge, not bridge, we got a for 3 pieces of land, and then we built 7 bridge across them. Okay. So is there a circuit that passes around Euler circuit on this town? So how do we solve this? We also can make this lane, right? This lane maybe called A, B, C, D into a point. So we string this connected component into a point. So maybe A, B, C, D, A, B, C, D. Okay. And then we make the bridge into the edges. So there are 2 edges here, and then 2 edges here, and then 1 edges here, and then 1 edges here. So 1 edges here. Okay. So use the theorem. Is there a Euler circuit here? Any Euler circuit here? No. Why? Yeah, because yeah. So there are no Euler circuit because degree of A, B, C, D are on. Okay? Yeah. Yeah, because they are. And what happened is, yeah. So there are no Euler circuit because the degree of ABCD are 3 and 5, I think. Yeah. Okay. So I did some reading on this bridge problem, and then they found out that actually this town undergo a war, and then 7 bridges are destroyed. And then what they're left with is these 3 bridges now. So there's now 7 bridges. Okay. Let's take a break to 9:58, and we'll come back for that.
这个 multiplier agent 是指什么？就是
那什么？
multiplier agent
哦，
是指两个点之间有多条线。
哎，对啊，对啊，对。
如果打人的话，就说他还有个对啊，但真正的日比不是卖如果你不是有就是最后真的，如果他达到这种一点的话，然后就是他从这边哦，那边比，就是当就讲要每一个那比较有
哎，你们学的那个 algorithm 跟那个书给的会一样吗？你们学的那个 algorithm 跟那个书给的会一样？
因为实际上觉得我们就是他有给我们放 graph 的 node，
对，跟这个会一样吗？不一样。哦，这是 construct 哦，对 construct 对。
这个就是他是去过一次那个 node 就不可以再，我好像也是有类似，因为我们是就是你看它是7个点，不那个3个点，
然后
不4个 node，
呀
1、2、3、4，然后就从这个 graph 出发，这是一个 direct 的方式，就它每条路径算走一次吧，走一次我就淘汰掉，最后发现我连不回去就找不到了。
所以不是这样子。
number 这个是，如果你的路是话，如果你是 H 差不多
一样。
对
OK
就是 H 吧
OK
，H 我用一次我就去除掉那个选项，然后我4个嘛，我随机挑4个，然后到处走 ，OK， 发现到最后跑来跑去不行。老师真的是砸掉那个桥啊！
那7条桥被砸掉。
可惜了。
然后
现在又是一个明显理由是，
你这里还有个你要有2个的话，
现在是那个 Russia 的，在 Russia 里面，之前在德国。
要不你有2个不一样，这个是好地方。
这个
2个
不知道现在在俄罗斯里面，之前在德国，在那个 Euler 那个时代是在德国。一个繁华的，因为它要接3个方案。
这个地方，就一个小岛。
然后那个刚刚那个地方，
哎，
这个 13是我一定要从它底，然后从它中，因为那是可以重复的。如果不加那个限定条件的话，
什么可以重复？
就是这个叫这个东西，
对，
是从它始从它中中间的路线，就是这个
对
是可以重复的。但是如果加了就是我可以重复的。
对。
那我加了这个限定条件，
对
就是不能重复。
不可以重复，对。
但如果 pass 的话，我不一定从它始从它中可以连接任意两个点，但是是不能重复的。
Euler path，Euler，
然后刚刚那个
就是每加这个限定条件的话，那个 EJ 也是可以重复的，是吗？
对。你是子阳是
后面有一个
子阳，
还要有两个
我怕我记错吧。
的话，好
OK，
不一定就没有设计到，因为它有两个
一个有哦就不能找到，一个有升级这两个都是对的，你看那个头的。这边是
那就不要了，这个。Yeah, pass down the attendant is 哎，
这个前面这个可以再翻回去的。
这样。
因为是加
是挺大的啊？什么？
加2，对，这个加1加2怎么回事？那个 degree 在
啊，对，
为什么没有加1？
加一是说，我从这里出发吗？我从这里出发的时候，不要写啊，对，starting X 跟N terminal X
哦，然后这边加2是因为
因为你进了出了
这边进，然后这边再出
，yes，
这边进来这边然后再出，
yes，
然后这边，哎，这边加1呢，是这边，因为这边出，这边是这样子，然后这边是这样子。
啊，对，这个加2是给他的，不是他的。如果你要他的话，你要再写。
然后总之就是那个 degree 就是看那个 number of edges，
对
它的那个进出
的
的
，yes，
有多少个 edges 在它的那边出来出去。
yes，对，叫 incident。OK，next。Okay, next, there's also a way to determine whether a connected multigraph got an Euler path or not. Okay. What's the condition? Hey, please don't sign for your friend. Last time you signed for your friend, right? I also have to check who haven't taken the exam. They also can't find me themselves. So you don't sign for them. They will come find me automatically. Don't sign for your friend. They will approach me themselves. Okay, so how to check whether a graph got an Euler path or not? Okay, but not an Euler circuit. Not that every Euler circuit is also an Euler path, right? Every Euler circuit is also an Euler path, but now we don't want the endpoint and the starting point, the terminal vertex and the start vertex is the same. Okay, so when do you have an Euler path? If and only if it has exactly 2 vertexes of odd degree. Okay, why? You know why? Huh? Okay, yeah, cannot go back to the starting point. That means this 2 vertex of odd degrees is exactly the start vertex and the end vertex of your Euler path. Okay, so this is the strategy here. So one direction is easier. Okay, one direction is easier because, like what we said just now, if you start from A, okay, start from A, you automatically got 1 vertex, and then whenever you pass through the other path, you got a +2 degree, okay, and then you end at B, okay, end at B not equal to that. Okay, so that's a +1 here. So in the middle, maybe you can pass through A or pass through B again, that's fine, but it's a +1 +2 thing. Okay, maybe okay. Okay, I just draw some example up for you to imagine. Okay, so let me write this color green for clarity, the degree. +1 here, and then +2 everything else. Okay, make sense? Okay, so the odd degree precisely because you start from the vertex and then you end at the other vertex. Every time you pass through a vertex, you must add 2 because you go in, go up, go in, go up, go in plus 1, go up plus 1, so it's 2. Okay, then the other one is hard, right? Because start from degree, you need to tell me construct an Euler path. Okay, a bit harder, but there's a clever way to do it. How to spell clever? No, okay. That's a clever way to do it. Okay. So there's one clever way to build this Euler path. Okay, can you think of one? The hint is use the previous theorem. Can you think of one? So if it only has exactly 2 vertex of odd degree, the rest are even, how you gonna build this Euler path? Hint is use the previous theorem. Previous the Euler circuit one. It's if every vertex has even degree, then you can build a Euler circuit. Yeah. And then this is what you want to think. Want to prove this. So how you produce the Euler the idea? Any idea? So what you can do is break. No, not break. So let's say A and B are the odd degree vertexes. The rest are even, right? So to use the previous theorem, you need to make sure all the vertex are even. Okay. So what you can do is you join the 2 odd degree vertex. Okay. So you consider a larger graph by joining the 2 odd degree vertex. Then they become even degree. When they become the even degree, by the previous theorem, you can find the Euler circuit. Yeah. So should I write it out or not? So we should consider a larger graph by adding the extra edge AB, where AB are the 2 odd degree vertex. Okay. Then all the vertexes will have even degree. Okay. Hence, theorem before, we can form an Euler circuit for this larger graph. Okay. So how to get the Euler path? You just erase the extra edge. Why is it an Euler path? Because Euler circuit already passed through all the edge exactly once. Okay. Make sense? Make sense? Okay. So just erase the edge AB to get the Euler path. Okay. Okay. Okay, good. Thanks. Okay, this one. Okay, use the theorem to test whether this guy got Euler path or not. Okay. Does G1 has 2 odd degree vertex? Which one? B and D. How about G2? B and D also?
Yeah.
B and D also. G3?
No,
What do you mean by no?
they are even.
Huh? How many odd? 1, 2, 3, 4, 5, 6. Too many. Okay, you can only have 2. And then these 2 is exactly how you build your Euler path. So you should start or end with these 2. Okay, let's try how to build this Euler path. So we start from B or D. Which one you pick? What do you want? C. Cannot start from C. Cannot start from C. Must start from B or D. B or D, huh? B, huh? Okay. B go to A. Okay, there's one way to go B or A. And then C. Okay. B. D. You see? You start from B, you must end with D. If you start from D, you must end with B. If you start from C, you go nowhere. Okay. Yeah. How about G2? B. A. Only one way to go. B again, okay? C one way only. D. F only one way. E. D. Okay. D only one way. Then F E. Okay. Good. Can. Yeah. Okay. So the 2 odd degree must be your starting or ending point. Okay. Done. This one done. Euler path done. Euler circuit done. Okay. Next one is the the Hamilton path. So this one is something to do with the vertex. So a simple path in the graph that passes through every, okay, now it's vertex. Just now it's X, now it's vertex. Exactly once. It's called a Hamilton path. Okay. So similarly, you can define for circuit. I think I don't need to repeat already. So you just change your path to circuit where you want to start and end at the same time. Similarly, for circuit. Okay, so this question grew out from Hamilton. So Hamilton want to visit 20 cities without revisiting the cities. So he draw these cities and then link them together. He got this dodecahedron. Yeah, dodecahedron. So he put the cities on this vertex. So there are 20 of them. You want to visit them, but without revisit them. Okay. So what you can do is you can smash this dodecahedron. You see, you smash it down, and then you become flat like this. Can you imagine or not? Cannot? You see, you see this hexagon here. Okay. What? Okay, you see this? See this hexagon here? You can imagine this hexagon here. And then there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Another 5 hexagon here. So you smash it down. Like you smash the tin, cola tin. Smash it down, flat, become like this. So how many faces you got? The dodecahedron. I think it's 12. You can go and compute. Okay. So is there 12 faces here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So where's the 12th face? Yeah, the whole thing. Very good. Okay, yeah, the whole thing. Okay. So this is the dodecahedron, and then Hamilton managed to come up with the solution here. So it's in your book as well. So something like this in the blue. Okay, so you can pass through all the 20 points without revisiting the point again. Okay, let's try this example here. G1, G2, G3. I let you try for 2 minutes if you can find any Hamilton circuit or you don't need to go through every edges, you just need to go through vertex. Maybe there are more than one Hamilton circuit that you or path. Probably more than one you can. Anyone try? Still home or try? Huh? Try, bro. Does G1 got any Hamilton circuit? Yes. So go from where? A, B, C, D. Okay, this one is a direct one. Okay, most direct one. How about G2? Only from Hamilton path. Okay, so A, B, C, D, E. Okay, because any circuit, you need to like go back to A or come out from A. So you need to pass this AB twice. Okay, so you need to like, you cannot avoid revisiting B. How about G3? No circuit, no path. Okay, no Hamilton. Why? You should go and keep trying, and then you will see that every time you want to do a path or circuit, you need to revisit either DC, AB, or EF twice. Okay. So yeah, you come back. Okay. You need to come back. So either way, you must use AB, DC, or EF twice. Okay, so you must meet a certain vertex twice if you try to draw one. Okay, so what are the conditions for the existence of Hamilton path? Or what are the what are the conditions? What are the necessary condition or sufficient condition for the existence of Hamilton vertex? It turns out that there's no easy answer to it. Okay, but few properties we can consider. So, for example, a graph with a vertex of degree 1 cannot happen. Degree 1 cannot have a Hamilton circuit. Does that make sense? Because you need to return to the vertex, right? Because it's a circuit. So you got degree 1, you cannot have a Hamilton circuit. I think this is also true for Euler circuit, right? As long as you got a circuit, because you need to return to. Okay. Okay. So next. So the next one is if a vertex in the graph has degree 2, then both of the edges have to be both edges have to be part of the Hamilton and circuit. So any Hamilton circuit. Okay, because that's the only way you can pass through the vertex. Because your vertex only have degree 2. That's the only way you can pass through your vertex. Okay. So any Hamilton circuit must pass through the 2 edges. Make sense? Make sense? Okay. So next one is because you only pass through the Hamilton, pass through every vertex one. Let's say your vertex got higher degree. The rest of the edges, actually, you don't need to consider any. Okay. So when the Hamilton circuit is constructed, then all is constructed passing through a vertex. Okay. Then the all remaining edges you don't need to care anymore. Because that's the only chance you can. That's the only way you can pass through the vertex. If you come back to other edge again, you need to pass through the vertex again, which you don't want. Okay. So all the can be removed. Consideration. Maybe I give you an example. It's easier. Okay, let's come back to this example. What is this doing? Oh, this one doesn't have. Let me is this one is a wrong. This first. Okay, so just now we consider the Hamilton circuit, right? So when we pass through B, okay, actually this part here, we don't need to consider anymore. Because if your path have to come back again, then you need to pass through B again, which we don't want. We only want exactly one. So once you pick a choice, maybe you pick this choice, then this one you don't care anymore. And this is what it means. Okay. And then, yeah, this is also a Hamilton circuit, different from the ones. And this is not a circuit, right? This is a path. Yeah, this is a path. Yeah, this one is a path, not a circuit. Okay, then in that case, it's another one. Okay, yeah. Okay, so these are the Hamilton circuit. There's two graphs here. We can decide that it doesn't have a Hamilton circuit, right? Because this one got a degree one vertex. Okay. Then you have no chance to come back to E again. Okay. If you come back to E, you need to pass through E again. Okay. And then this one, why doesn't have Hamilton circuit? Okay. Because A, B, E, D has degree 2. Okay. E and has degree 2. So that means all these edges you need to use. But if you use all these edges, right, it means that you have to pass through C twice. Okay, you can try out. Okay, see, twice. Okay, so you cannot avoid passing through C twice. So there's no Hamilton circuit. You only can pass through each edges once. Okay, except the nothing important. Okay. So far, okay. Okay. Yeah. So some example is like the complete graph. You can find Hamilton path starting at K3. This one, I mean, path can, but circuit have to start from K3. Okay. You see K5, right? Got two Hamilton path. You can draw the star. You can draw stars in. Okay. Not just the boring cycle here. Okay. These are the cycle. This one got path, K2 got path, but not circuit because you cannot come back. Okay. If you come back, then you need to use it. Okay. Hamilton path, Hamilton circuit. Okay. So some theorem they discover by O. So you also can check on the degree of vertex, but a bit tedious because you need to check the sum of pair of them. So if you check that every two degree of every two vertexes, the sum is greater than the number of vertex, then you can find the Hamilton circuit for every pair of non-adjacent ones that cannot be connected. You need to check for all non-connected ones. That means you need to create enough room for you to build the circuit because you don't want to revisit the vertex. Okay, so you need to have enough edges for you to build to avoid yourself coming back to the same vertex that you pass through. Okay, but we won't prove this. But there's one corollary by Dirac. So I think Dirac's is easier to check because you just need to check for each of the vertex. So Dirac show that as long as the degree of each vertex is at least 2n/2, okay, more than half of your vertex, then should be fine. Then you can find a circuit that doesn't pass through, that passes through every vertex line. Okay, so you need to create enough room for yourself to avoid passing through the same vertex that you have passed through. Okay, so the moral of the story is you need to have enough edges. Okay, but maybe you can ask whether these converse are true or not. So if you got a Hamilton circuit, is it true that the sum of the degree is greater or equal to n? It turns out that the converse of the all theorem is false. Okay. So the converse theorem is false. Okay. So first, using the easy example, simple example, so the K5 example. So this one has, so the converse is what? If you have a Hamilton circuit, I want the non-adjacent vertex to sum more than or equal to n. So if it is less than n, then this converse is false. So this one, this K5 has a Hamilton circuit. Right, just now we discussed it. So you just take the circle. But if you take any two non-adjacent one, you add them together, is what? Is 4. Every degree is 2. So you add them together is 4, which is less than the number of edges, which is 5. Okay. So the converse is false. Okay. Similarly, it is false for Dirac theorem as well. Okay. Because every degree is 2, which is less than 2.5. Because Dirac said is as long as you have more than half of it, you can find the Hamilton circuit. But less than half of it, I also can find the Hamilton circuit. Okay. So there are two ways to check whether you got a Hamilton circuit or not. Doesn't tell you how to construct it, but just to check whether it exists. Yeah. So far, okay. Hamilton circuit. Okay. Next. Next we talk about planar graph. Maybe you ask what's the application or what's the idea behind planar graph. So what's the idea behind planar graph? For example, you got 3 houses, okay? You got 3 houses. And then you got different utilities here. Okay, you want to build cable or pipe to your houses. So is there a way to avoid the intersection of pipe and cable? Okay. So we don't want the pipe to intersect with the cable, right? Or even the this one you use one. But this gas pipe. Okay. So you don't want the gas pipe to mix with the water pipe or the gas pipe with the electricity cable. Okay. But in 3D it's fine, right? In 3D you can just lift up the intersection. Is it okay? But 2D we don't want 2D have to intersect. That's why we call it a planar graph here. So we want to consider it in 2D. So what's the definition of planar graph? So a graph is called planar if it can be drawn in the plane without any edges crossing. Okay. So if it can be drawn without edges crossing, then that's fine. And then such a drawing is called a planar representation. Okay. So for example, let us ask. Is this? I think this one is the K4 graph. Is this planar? Is this planar? Who's anyone? And no one. Is this planar? No, because got edge crossing here. Last week we learned isomorphism of graph, right? So we can redraw this graph. Okay. So in this way, so it's not crossing. So that's mean as long as you can find planar representation, planar representation of the graph such that there's no edge crossing, then it is planar. Okay. Remember the isomorphism, just to make sure every vertex is connected the same way as before. Okay. And I just bring this this line off. Okay. This is a graph I saw. Okay. So it is planar. It is planar because it admits planar representation, which is the way of drawing graph that is not intersecting. Okay. 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 Similarly, for this graph Q3, right? You can see that there's edge crossing here, here, right? But is it planar? Yes, because if you smash it, okay, you smash it flat, become like this. This is also a graph isomorphism, so there are no intersection. Okay, so this is also planar. Q3 is also planar. Maybe you can ask if is any example that's not planar. Okay, so this one is not planar. The complete bipartite graph of K3. Complete bipartite. From three vertexes to three vertexes. It's not planar. Okay. So how to see this? One way you can do is try and move them around. Yeah. So one way you can move them is this. Okay. What did I do is I take this vertex, yeah, and I bring it down. Yeah. So I take this vertex and move it down. Okay, make sense? Okay. So the next thing is you can see there's still intersection, right? So the question is, can I reduce this intersection? So where can this point go? Okay. So how many regions you got? You can either put it outside, okay, or put it inside here, or put it on this side, R2 or R3. Okay. So either you can move this vertex around here, okay, or you move this vertex into R2, or you move this vertex into R3. Yeah, there's three places you can go. But if already outside here, you can see that you cannot reduce this intersection here. And similarly, if you move it here, move it here, move it here, you will have a lot of intersection, which you don't want. Let's say we move it into R3. Okay. See what happens if we move it into R3. So move it here, and then we got connection to this one, and this one. Okay. Can see that although we managed to reduce intersection here, okay, but you can't avoid the intersection here. Okay. So similarly, if you move it to R2, you will have the same story. So you, no matter where you move the vertex, you cannot reduce your intersection or the edge crossing. So K33 is not planar because it doesn't admit any planar thing. So if you want to show that it doesn't admit any, you need to try all the possibilities. But you want to show it planar, you just need to find one. Okay. Yeah. So far, okay. Yeah. Okay, next. Next. Okay, next is this powerful formula here. Okay, this one is very close to my research stuff. So it's called the Euler's formula. Actually, Euler is a mathematician all days. He get blind during the old age, but he still can do research and write long paper because he memorized all the formula, all the theorems. Still can calculate even though he's blind. So let G be a connected planar symbol graph with E edges and B vertex, and then let R be the number of regions. Okay, just now we only see the regions bounded by this graph. So the formula is R equal to E minus V plus 2. Okay, so I want you to believe it first. So let's draw some example. Okay, what example you want? Okay, I give one simple one first, then you give something else. So let's see the triangle. Okay, triangle got how many regions bounded? So got R1 and outside R. Okay, so the formula is R is equal to 2, E is equal to 3, V is equal to 3. Okay, so is 2 equals to 3 minus 3 plus 2. Okay, okay, good. So maybe you think that this is simple, right? So maybe we do something crazy. What you want? Something like this. Okay. Okay, let's try this. Let's try. So maybe you got R1, R2, R3, R4, R5, 6, R7. Okay, so our R is 7. E is 1, 2, 3, 4, 5. And then V is 1, 2, 3, 4. Okay, E is how many here? E is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. E is 5. So 7 equals to 10 minus 5 plus 2. Okay. Okay. Yes, yes. So what's wrong with these two? Why plus 2 everything become correct? So this tool is a magic tool here. Okay, actually there's a name for it. We call it a Euler characteristic. Okay, so Euler characteristic of a planar graph is 2. Yeah, so this is the special number Euler characteristic. So actually we can associate this Euler characteristic to any surfaces. It turns out in this universe, okay, there are 3 types of Euler characteristic you need to consider. So there's Euler characteristic of surfaces. Either it's 0, greater than 0, or less than 0. Okay, only 3 group of them. And then the 0, 1 we will call it flat. And then greater than 0 is spherical. And then less than 0 is hyperbolic. Okay. Yeah. So depend on the gravity, the surface that appears in the universe will be either one of these 2. Okay. Yeah, why is it spherical? Why is this called spherical again? So actually the Euler characteristic of sphere like this is, and yeah, it's same as the planar graph. Like yeah, so yeah, for example, the cube is also 2, right? Okay. So if you like smooth the edges out, okay, you smooth the edges out. So you smooth it, you smooth it, you smooth it, smooth it, smooth it. And actually these 2 are the same. Okay, never mind. Just for some extra knowledge. If you smooth the polyhedron is actually a sphere. So this is what we call a topology. But this one extra, never mind. Just for some story. But we won't prove it today, I think, because it's today we don't prove it. Maybe we'll do it next week. Okay. Yeah. Okay. Maybe we'll come back at 10:56. Then we will discuss exam. Okay. Hey, still tell Sung Hon haven't signed up. Huh? Yeah. Ah, yeah. 不同的东西。
它不都是
planner 一个交叉。
哦，它都是
planner graph 是 graph，那个 Euler 它是那个你可以走的路径。
这个是
这个是那个 graph 的特性。
别人的 graph 是不能交叉。
它的
它的 H 不可以交叉，但是可以
重复的意思。
不走。
哦，paragraph 不是在走 paragraph 是在指那个 graph 的特性，就是你可不可以画那个 graph such that 那个 H 没有表那个。对，但是你要知道，你可以，比如说这个，你看，就算它有交叉，不是，只要你能够画得出它是一个没有交叉的形式，它就是
是我们变成保持这个点的这个。
对对对对对，呀，但是这个不行，是
这个就是让它变了。
你不管怎么变，它还是成。
就是
OK。
想问一下这个
啊
connect 的那个定义我反正不太理解。
connect 的定义啊，connect 的定义就是说你拿每两个 vertex， 你都有一条 path 可以连接。OK， 你讲一下。第三次是 Come get your test paper one by one. No sample. I can't get your exam paper. One by one.
Last 3 digit.
I'm 821.
821. Yeah.
608.
bro. 821是哪两个？你班谁呢？OK。
601.
Because I need this physical paper back. You can take photo. 948. $97等下不见掉，我不知道哦。不见掉，我不能够改错的。I got lost the paper, right? If lost, I cannot add mark to the.
你可以到前面读上，有三四109，我们快问。
然后
要还我不见掉，我们改。
96.2，因为我们
Last 3 digit.
我自己
这个是97
啊？
后个长分。
导演会跟。
一直有。
可怜吧？
谁是678？谁是真的？都那都在都在他们家都在。啊，尾号2开头。还有一个。
现在人嘛，
一个
93，还有
93次。哦，展国。
93最好，那个帮看。
就是。
934。对的。
啊。后面的吧。
然后就差不多943。
有可能。
大家这个是有啊，有没有934这个？哎，有哦，哎，居然是934哦。
啊，
你们哪说的？
那你开始看起来了啊
93咯，yeah。
这样子。
Okay, you can read and then we will discuss and then you can take photos because you need to return me the physical so that I can change mark later. Okay. I need the physical one to change mark, so don't lose it. If you lost it, then I cannot change mark for you. Okay, let me bring out the. I think I will use the first exam to discuss Kun Zhijian, if you want to see the answer, you can find me. But general question is the same. If you want to see the solution, you can see later. So I use the normal one to discuss first. So let me first. Where's the Google Drive? And then don't you can make a note on your other place, don't make note on your question paper. And then if you want to claim mark after we discuss, you can. Yeah, but don't write on the paper. Don't write on the exam paper. You can write somewhere else, but don't write on the exam paper. Basement. Last three digit. Last three digit. Last three digit. Hello? Okay, let's see. Okay, let's discuss now. Don't write on your exam paper because they have to send back to you. Okay. So first question, true or false? So true or false, I put 2, 3, 3, 3, 3 marks, right? So 3 marks mean you need to explain. Yeah. If you don't explain, you won't get the full credit. Also already warned you at the start. Answer without step would be given. Okay. So first, if you are in doubt, then you should move on to the next question. Yeah. I said that this is not a proposition. This is a command, so it's not a proposition. Yeah. So it's false. It's true. Yeah. It's not a proposition, so it's true. Actually, this question already I hint you that you don't stop at the question too long. So just keep moving. Two. If you change the order of your quantifier, they don't always give the same true value. So if you want to prove something is false, you should give a counterexample. Okay, counterexample will work. Three is some trick question here. So I take a union of an empty set. A lot of people say what empty set is not a set. Yeah. So there's no element here. So if you take union, you still get back your original set. Okay. The flow function is injective. So it's not injective because you have two different numbers that get sent to the same value. B actually we discussed this before, but it's in the contra positive way. If A divide BC, then A divide B or A divide C. This is what we did in the class. I just put it as a contrapositive. So it's false, right? Similar if yeah. So if 6 doesn't divide 3, 6 doesn't divide 2, but 6 divide 3 times 2. And in class, we discussed the contrapositive of this segment. It's also false. So far, okay? This section. If okay, we move down to the next one. Okay, so far, okay? Jot down anything that you want to plan later. If I miss anyone. Okay, yeah, question. Maybe I will upload it later. Yeah. But I mean, for now, you can write down. But yeah, maybe I'll upload it for later. Okay. I will upload it later. Okay. So next 2A. 2A is just testing the truth table, whether you can use truth table or not. I think most of you can do it. Some of you do it half of it because there's 3 here, so you need to do for 8 instead of 4. B got a few ways to prove. If you want to use truth table, also can. If you want to use algebra, also can. Okay. If you want to use contrapositive, also can. A few ways to prove this. And then C is a bit tricky because I restrict the way to prove C, because you can note that A and C is the same statement. Okay, one use truth table, and then C I want you to use B to show. Okay, so I force you to use algebra way to prove it. Okay. So algebra way is like using the law I given in the back. Okay. So 5 marks around 5 steps. Okay. So the marks is given based on how many steps you need to write. I don't simply give mark on. So the marks will be based on how many steps you have, you need to do around. Okay. Is it okay for question 2? Question 2, okay. I move on. Just stop me if you want to see. Okay, question 3A. 3A. 3A is about induction proof. Okay. So both of these questions can use inductive proof. But both of these questions also got students don't use inductive proof. But it's fine. For example, they prove this for general cases. So they just look at the general formula and then show that you can write it in the n hash n form. Some of you also can show this without using the inductive proof. Using the counting way. We haven't reached counting yet at that time, but some of them know how to use counting, so that's fine. They said that whether one element is in the set or not. So there are 2 possibilities, or 2 to the power of n. Okay. So my way is use inductive proof. So you need to check for base case, assume inductive hypothesis, and then use inductive step. I think only one in your class use this way to prove. You split the subset into 2 kinds, whether they are built out of the n element, and then the other one contain the n plus 1. I think only one of you use this method. Yeah, I admit this one is a bit tricky. I mean, for 2. 1, you have to write it out to see. Okay. Okay, for question 3. Question 3, okay. Okay. Question 4. Question 4 is logic. So whether asking you what's not C implies not S? Is it inverse? Yeah, inverse. So whether asking you inverse of the segment and the segment are logically equivalent or not. Okay. So some of you going too far. Too far meaning you break this sentence into too many variables. Okay, so that's why you seems a bit confused here. So what you should observe here is, you see, contradict this or this. Okay, so that does not contradict this or this. Okay, so you should like regard this sentence as a not of this sentence here. Okay, so this all you actually don't need to care too much. That's why I put a C here. I want you to see it as a proposition, for proposition, and then for proposition. Yeah. And then surprisingly, this one, a lot of you got it. A lot of you got it, this one. Okay. Some doesn't imply all, so you cannot conclude for anything. Okay. Surprisingly, this one, most of you got it. Yeah. Yeah, this one string theory. Yesterday I changed into superstring theory from Boom for Zijian. Similar question. Answer also the same. Okay, 5A here. At first look, this one is quite hard, but if you split the word, okay, for example, split this given, split the exist, and then split the if, and then you should know what quantifier you are using. Okay, this is I think first week or second week stuff. Second week, given, and there is this. Okay, and then this condition here already, I write almost everything already. So you just use this notation, just use this notation. And then less than. Okay. And then the B is to test you whether you know how to negate quantifier or not. Can you do negation on quantifiers? De Morgan's law for quantifiers. Okay. So for every become this become for every. Okay. And then imply becomes P implies Q become P and not Q. Yeah, this is what I want to test you. Some of you even change this thing, or you say that they must not exist. They exist because they must not exist. Okay. So this one is testing the De Morgan's law for quantifier. So if you can write out A, then B should be obvious. So this is the question. Yeah, 4 marks will be given if you give the right quantifier and then give the right condition and then give the right implication. Okay. Yeah. Okay. Question 5. Okay. Okay, I keep going. Okay, question 6. About set theory. Just want to find intersection, find the cardinality. I still found that some students still don't know what's cardinality of a set. We already did it in the quiz as well. Okay, 3, work out the power set. This one, a lot of people, what they did is they forget the empty set. Okay. Or they don't put the set notation for this singleton. Okay, they just put 2, 3, 7. So these are all set. Okay. And then for I think most of you that can calculate did the right thing. Okay. So what is the Cartesian product? So you need to take all the element in A and then comma with element in power cell B. So if you do that, it's just a multiplication. So after you learn the counting, this one should be more obvious. Okay. So if I think if you calculate the wrong cardinality for power cell of B, but you multiply them, I think I still give you marks. Okay. I still give you marks because you just use the wrong number, but you know how to calculate, so I give you. Okay. Okay, for question 6. Question 6, okay, then we move on. Question 7. Actually, this part 1, right? I I already stated in the class, but I didn't prove it. And then no one asked me about it as well. So I give you a lot of time to think about this question in the class. So how to prove that any strictly increasing function is one-to-one? So you just prove one-to-one. If fx equal to fy, then x equal to y. So you can try prove the contrapositive. If x is not equal to y, then fx is not equal to. Okay, let me write it down. So one-to-one is if fx equal to fy, then x equal to y. Okay, so contrapositive, you can equivalently you can show if x not equal to y, then fx not equal. Okay, so suppose fx is not equal to y, then there's two cases, whether x greater than y or x less than y. But these two cases are symmetry, so you just need to do one. Suppose x less than y, then by strictly increasing, you know the fx is strictly greater than fy, then they are not equal. So done. Okay. Show that it's part 2, show that this function is injective. So my hint is to ask you to show this is increasing first, and then you by part 1 it is one-to-one. Okay, actually I put a bomb here. I bombed myself. I thought this one is subjective. So the first question, first answer I met is Chris Nandi one. Chris Nandi found that this is not subjective, and then I go and check. Oh, yeah. I set the wrong domain. So this one become non-subjective. Yeah. So actually it's not subjective. I bomb myself in this question. It is not subjective. If you put this question equal to 1, then there's no pre-image. Not subjective. Okay. Any question on question 7? No? No. Okay, we keep going first, and then if any question we can come back. Okay. Question 8. For EA, if Euclidean algorithm, find M and N. This one is a standard question, tutorial question as well. Also lecture examples. I don't see there's any reason you can get wrong, but some of you still get wrong. That means you didn't do the tutorial or even understand the lecture example. So I also can't help if you do that. But most of you got the full mark. Okay. Maybe some careless mistake. You don't put the minus, you just print the 8. Okay, this one I think is the less problematic one at A. 9A. Okay, this one a bit tricky. One still okay. You just okay. Some of you put 3 here, right? So you mod 17. For example, okay, I don't know how to say. Yeah. So if it is divisible, it will become 0. Okay, not the you call that dividend, not the dividend. Is it dividend? Yeah, dividend. Okay, B. This one a lot of people make mistake because I didn't say that. I didn't say what? I didn't say that n and 35 is co-prime. Okay, so you cannot just straight away use the AP minus 1 equals 1. Okay, what you can use is AP converse and prime. Okay, because I didn't say that AM is equal to what? CD of A. So cannot use AP minus 1 equal to 1. Okay. So yeah. So that's it for this one. Yeah, a lot of people use AP minus 1. But there's no GCD AM A equals to 1. Okay. Yeah, this one is also a variant of a tutorial question. Okay, 10A standard Chinese remainder theorem. Hey, but this one the people didn't use Chinese remainder theorem. They test the number. There's only 200 to 250, right? They just test the number. My range too small. That's why I changed my question in the Jian one. So that they cannot test the number. Yeah. Yeah. So they just test the number. Yeah. Okay. So Chinese remainder theorem, how to use? You found the M, capital M, and then a lot of mistake in finding the M bar. So you thought M bar is just what you think is like 20 mod 3 is the M bar, which is not. This is the inverse. This is the inverse of 20 mod 3. This is the number that multiply to 20 equal to 1 mod 3. Okay. So it's not just 20 mod 3. Okay. And then some of you forget to change the answer into the range. Okay. So you just keep the originals. Okay. Any question? Other question you want to run through, or you got issue? So the scale I will do is, I think, if no mistake, I will do your mark times 0.7 plus 30. Because I don't want to fail you in this midterm. But if your midterm is less than 30, you need to be careful. Okay. I can't save you in final, or I can't save you in quizzes. If your midterm is less than 30, I think it is quite dangerous. I think above 30, you can still work hard in your quizzes and then your final. Okay, the result of this scaling, right? I will scale up. I think above 80 will move to 4.0. I think this is one of the consequences. At least move out a grade. At least move out a grade. Okay. Yeah. Yeah. 应该是 yeah. Okay. Yeah. Yeah. Okay. Okay. If your midterm below 30, you need to be careful. I think I cannot save your quiz or final. OK。呀，问呢？什么问题？第八题，第八哈。Question 8. As long as you have the right step, and then you got the right answer, you get a full mark.
20的，可是后来拿到吧，我就只会
什么意思？
20的话，因为是在碰老师应该做最后，我的我弄得比较差一点。
对。
然后出来答案一样，结果是啊，就是他应该是没拿满的地方就
不了，怎么扣你分？为什么扣你分？是因为你这个东西乱用，你从上面就开始乱用了。你这么忽然间这个，你用的这个 law 不是 implication 哦，是那个呀。不会，扣一分吧。你知道你什么错吗？先。
那个等，还是因为我们就是多了
啊，对，所以你还有一些东西没有写出来，你知道吗？你还有东西没有解释清楚。对，你用了逻分，然后你还有东西没有解释清楚。啊，对啊，我上次看错了啊。
我这上面写的
先看一下电脑有没有错就可以了。在哪里？不是
077
姓什么？
陈被
哎，没有啊，看错了啊，我看错那个方，这是别翻的。你们是 group one 的。
077后面。
哦，每个啊，
这个你是哪里？
其实没有说你用什么。哦。
啊，然后这一步就是这个。
这部分，
对啊，这一步就以此推的，然后后面这一步用的是这个。不好意思，
不是，这个是什么？
就是它能推出来，然后
它代表。
然后因为我们第一份知道这个，所以它能推出来。
啊，写有点乱的。这个呢？这个去这里呢？这个就是它嘛，这就是它嘛。
对啊，这个就带过来了，然后这个是第二份的那个结论，这个结论是用在这儿，这个是最后面这个推理。
然后这些中间呢？
中间就是正常的拆开。
拆开你没有写，你用什么？
不用了，拆开这个括号
要，
不是，等，这个没变，这个就是把这个负号带进去。
OK， 这个我知道，没有。没有，你这一个是用这个，
对，
然后负号带进去。
对，我就简便了，没写而已。
要写。
不是，我这里面没变，最开始没变。
我知道。下一步
就是把这个符
号带进去嘛。
对啊，符号带进
去。
不，符号带进去呗。
符号带进去哦，不中啊，不然我这个音没有用啊。你看这个。拿什么？
就是我这个步骤很明确了呀。
我知道很明确，但是你要写，用什么？写一下用什么？然后你这边写的有点乱，其实。
对，主要就是
要写名称
名称，
呀，
名称这他们都写了吗？
有他们都写。
名称你们都写了？
老师有讲啊，
我问了
每一行都要写啊。对啊，要写。
我操，兄弟，我都记不住这个。
不是这个
用这样，
后
我没有给
用
用了什么？
这样的这个直接
不写完就没有，为什么要等？会扣一点分。
对，我感觉我
知道老师跟你讲要写，但是你只告诉我这个啊，但是你没有告诉我为什么。
这不就是 increasing function 的那个
increasing 是说大于啊，他没有写不等于，因为没有写出来。
那这个
哪个？
这个
这个我已经给到差不多要满了，因为这个是3分其实。
哦，
然后就是这一步，
没有啊，我这里正了，
那你自己在哪？
我这里打了个那个，就是用到了你这个嘛，
啊，对。所以你要用这个还是你要用这个？
就是
做这个我讲会
是用了这个之后，当他们等于的时候，他们就等于说是 inject。
不等于。就这个能够证明这个是因为不等于这个不等于。但是我想说就是这一步不可以这样直接下来，这步直接下来也不能够直接用这个。啊，
这个它少了中间的一个过程，它可以分解。
这个过程有点复杂，如果你直接下来的话。怎样？
就是我真的是这个东西是
对，
它是 increasing，所以说它是
你决定
one，
对，
所以说
它跟这个没关系，我
one to one，
因为你看你的 one to one 的这个证明是不等于证明这个不等于证明这个不等于，可是你这边是这边等于呀，倒反了，所以
哦，
它逻辑是一样，但是它不能够解释为什么这个等于这个就等于。
那我这个用这个直接证，
就可以。
那我这样不就是相当于不用这部分其实是对的
啊？对。这样你要吗？看一下102。对，如果你那个丢掉的话就不用了，但是我不知道你知道还是不知道。7哈，这个干嘛？
是吧？
对啊，这个还有吗？
这个只得2分吗？这个是4分是吧？这个
对，这4分吧。
那我写到剩最后一点。
没有啊，你只算出2个东西吧，要算出3个东西，然后加在一起就对了，就4分。
3个东西。
最后一个东西，这2个，1、2、3、4。
对啊，我算到18n 减1了，我就
你算了1个而已，然后你也没有最后答案啊，你也没有。
哦。
我说了一个，你就算了。这一部分是哪个地方？这个你没有算18 boss， 所以就没了1分。然后你最后也没有正确答案，又没画了个圈。我不是不知道。
我们都没有讨论过那个 strictly increasing 跟那个 gradient 什么关系？
第一题吗？我这有讲的第2题。
对。拿哪一个？等一下。
你给我，我知道你给我画这个 strictly increasing，因为我这有个等式。
对呀，
因为我这上面写了 for x 大于，
所以 strictly increasing 是要
对呀，它就大于0，因为它那个 strictly increasing。
OK， 下次不可以用上课没有教过的东西啊。
这不是啊，
都没有教过啊。
这有求导啊。
这门课里面没有啊。
这为啥不可以？
这样你就没有用到这一门所教的东西，对不对？
但是他那个等会儿
OK， 可以，我觉得可以。可以，但是你不可以用上课里面没有教过的东西，可以吗？可以吗？ 会用上课里面没有教过东西，我们都没有学求导在这门课里面。
老师你看，但是你这个是直接写的呀。
我这个是因为我用上面啊，
对，你就直接写的呀。
我直接写。
然后我甚至还给他解释了一下为什么他这个。
不，我的直接写是因为这个 hint 来的，你要写出来这个 hint 在干嘛？哪一个？这个 hint， 哎，我给你的这个 hint， 这个 hint 可以推出这个是这个 OK， 这个我可以加给你，我没有看到这个东西。但是下次不要。
就必须得用上课的这些东西。
对呀、不然的话你在哪里啊？哎，不是七，
快审对，这是快审期。
懂。哎呀，忘记了，七。OK。
可是我刚刚那个可以改吗？
一个就那一个吧，就这个吧，就这个吧。
还有这个是哪里扣的？
就这个吧。
还有这个是哪里扣的？
这个哪里扣的？这个你在做吗？你都没有在做到东西。
我挣的这个，
你怎么在？
是
我要挣它是不拖地。你要告诉我你这整个东西怎么回答，然后我才可以用。
那这个，
这个就这边不要了。你是102。我也这么慢说话。107。
你说40% 可以拿
可以，
就40% 可以得 A，这个
什么叫40%可以？
没有，这个是72分，72分刚好4.0。
72可以上到4.0。
哎，不是说70%加30%？
对啊，72乘了可以到80。你们的4分不是85以上吗？
你刚刚说的不是80吗？
没有，我是说考80的人可以上到85。
哦，那所以到底是怎么算的？
对啊，就乘0.73。
1加30，这完全没有分。
完全没有分。
我用的这个，它这个就是根据就是这层的都会有这个，然后
我这里给1分，因为你什么东西都没有解释，然后你也没有要，不然我用这个来读。
那种我要写是要写好，
没有用这个吧，这个
不可以
啊，可以用这个，但是这一个的话，我在上课有讲用，我给它一个名称。
没有，好像上了个60，我也不知道。
就是我上课有讲这个，就给一个名称嘛，就一个名称嘛。condition 就是你从 condition 变成 discharge， 对不对？但是你看你是在这边有用 Demogan's law，
可以参吗？
啊，
我肯定可以参呢。
什么叫不可以参？你可以参，但是你没有解释，没有解释。可以加1分啊，但是我不知道你在做什么的时候，因为你没有解释。
因为那时我没有想到要解释，我就直接去做，没有记得
要解释。除了这题还有
没有？因为我自己
你是什么号码？606。
我自己的位置是那种
第2题哈。
对，讲高分。
哎，606第2题。
那我拿
16哈。16啊。OK， 可以。加油！这个有分是5分。哦，对哈，这是 for 他。哎，对，我看错些。
来，老师一样的问题。
OK， 除了就这个吧，有啊，还有啊，
还有啊，
来，
还有啊，
一定还有，613，来，好来，
可是老师我很多忘记题目啊，
什么叫做忘记题目？
就我不能，
跟地题一样哎。
地题一样，就是数除
第几题？
数下面。
第几？
哦，
我
要跟你讲，你还不知道。
第七。第七这个错。
老师为什么这个不能？
怎样的呢？你这个是反来哦，你是反着做哦。你这个是反的，你看你是这个了才有这个，我们是有了这个才这个。
和上面
可以了，老师。
一分啊，
我
可以啦。
我现在
要比较好一点的，这样。
要好看点吗？
好看点，不能零分啊，老师。
老师不要笑我，不要笑我，不要跟我讲，不要跟我讲。
就我只是这里写错吧嘛，所以可能扣1分哦，剩4分哦，对不对，老师？
没有，这
这个我不能接受。
多低分啊！对，
你看老师，这个明明我只是写错这一半，不是？明明讲认真啊。
没有认真是要 support 这个。
还要讲那个 suppose 啊？
对呀。
哇，讲我那个。
可是我也是有写这个哦，老师。重点是这个不是这个 support 只是一个辅助嘛？
对。概念在就好。
老师这个算还好，请我来这里跟你辩论。
没有，他的概念只对一半。OK，
快一点嘛，快点。
老师
OK， 我看在什么份上 ？OK， 我看在什么份上啊？我看在你的份上，你是从这个开始，但是你写的时候，你不知道你从这个开始。
就我写德玛利嘛。
德玛利是很严重的事情啊。对呀，
可以多1分吗？
哎，其实我给了嘞，这1分就是那个1分啊。
不是下面的咩？
下面没有分。
那老师可能这个，
哎，我给了，这个1分，这个1分是这个1分来的。我给你
人家多1分啊，老师。
我们分过关。
越来越离谱了。
老师，这是题，如果他是的话，我这个就对了，right？如果，所以老师你要给分。
不能，我给你们全部30分。
没有老师，
老师都已经30了，再给多1分没有差。
喂，等下警察会抓我，警察会抓我。
马来西亚警察容易搞定。
警察会抓我，
越明显我做。
等下警察会抓我。
老师怎样吗？
再换
你再去找1分出来了。
可以，
我有
我一定找。
我这里不可能是0分。
哦。
你看，它是个东西，我这里应该是写的，我觉得我没什么问题呀。对呀，它如果是这个东西的话，那你如果 x 小于 y， 那 f(x 小于 y)，然后我就假设我找了2个不同的数 a。
OK， 我看一下，
你看看。
很热啊，真的。
哦，我知道了，你这个OK， 这题是4分是吧？
对呀。
我给你3分。
好
，1分是因为你没有从这个出发。
我 a 和 b 的呀 ，a 和 b 是2个不同的数呀。
没有。给我等一下。对，你有东西在这里，但是你有一些混乱在你的逻辑上。
是0分啊。
对，不可以是0分，但是我可以给你，我可以给你3分这个，因为你少了一个。
老师不能用那个4减1的丢率啊嘞。
就呀，你这边有问题，就是你要 start from 这个点 ，support 这个点。
我就觉得
我
是从这里开始的。这句话是解释它什么是那个 strictly
OK， 可以。但是你要从这个开始，不是从这个开始。
从这里呀 ，a 和 b 嘛 ，a 和 b 肯定是不一样的2个数。
那你要写出来，因为 A 和 B 可以一样，可以不一样。
好了。
然后你也不可以 support 这个东西，
那就先加这个。
OK。还有吗？
还有一个，前面也是个0分。
看一下你
103。
103，刚才你
就离谱。
刚才第几题？
什么？
刚才第几题？第7题。第5题。
这个第7题。
你是0分。哦，好，0分。
OK。OK，可以。
就还有一个这个题，我就是假设 可以看那个卷子上的题目吗？他不是要证明这个等式吗？我就是假设它是对的，然后我再把它加一个就是它是 n 嘛，然后我就假设它是对的，然后再 n 加1，然后去证明它是不是还是成立。就我加了一下，然后我现在把这个式子减去这一个式子，然后我看它等式两边是不是还是能成立。
OK， 好，可以。
然后我就
成立了。
是啊，我就这样子，就是等式左边去减去这个1是等式左边，然后右边去减去右边，然后就是这个地方是重复的话，然后就是1加上 HK， 然后右边就减去右边。
OK， 可以。
然后这个是0分啊。
因为我看过你在做吗？因为你没有做 base case 出来。你没有做这个 base case 哦，你没有查它的那个 base case， 然后我以为你是来乱做后面。
哪里是乱做？好好真的都是。
OK， 可以。So， 看一下啊，看清楚一下。
这个0分哦。
会有一方面，然后我想问他为什么不能去，可能我跟他解释。
你看我都说了他不太意思。
这个我知道，这个我知道。你这个左边右边。
对呀。
哦。OK， 可以。但你没有做 base case 哦，我加扣1分。
对呀，那个其他都是对的。
老师，我来了。
OK， 你。
我本来是对的。
对啊。
我开玩笑。
啊，1加5啊。
我操！好厉害！
这个是你啊。
不是1加5是6啊。第3题应该是。
6啊。
啊，对。啊，对。
那就这样。
谢谢老师。
OK。
要再回来，拜拜。
再去等。
对啊，这个很简单吧？这个 boss 有1分哦。
哦，是哈。
然后人就是有明白一个点，就为什么这个 H 不行。
我看到语分。OK。
没有，我这一个是。这个在 explanation， 我可以看在题目。
对。OK， 我可以给你2分，因为你这个没有给我一个实际的例子，只是形容有这种情况出现嘛。
那我给你个实际例子在旁边。没有了。
2分。OK。
我想问是这一题，这一题，其实我不明白为什么不能用 example 来做。
哪里？
这个。
哦，因为这个很简单，这个他讲 any 所有，但是有时候 example 不长这样啊，你明白吗？
可是我都放大给你。
我不是给你2分吗？
哦，2分是否这个人啊？
也
是否确定？
就是给这个 part 1。哎呀，对。
我在找。
这个有很多不懂，因为这个formula是我自己写出来的，虽然讲那个答案是错的，我想说哪一分？
这个不能8分，
我们的要拿1分。
因为其实讲真的，它就是跟本来的那个 concept 一样，只是我的这里错，所以我上错东西进去，我答案没错。
但是你找错这个 M100、M200、300。
但是我打进去这个 formula 的那个 concept
但是问题是你用错 formula
啊，用错 formula？
因为这个 Y1不是这个东西啊，所以我才不要给你分。第二个我不要给你分的地方是你这么停在420，如果你停在200跟250之间，我还可以给你分。
啊，也对啦，也对。
就这样。OK， 可以，没有问题。
老师，这个放进去啊？
啊，放，可以帮我排一下，可以帮我排一下，可以帮我排。就
学号
啊，学号。
老师可以帮我看一下这个印象可以。这边来，这个 这个 strictly
呀，对，对，要这么
就能嘛，这样子的话，
这是什么东西啊？
就因为如果是 one to one 的话是这个 condition 嘛，然后我就把它 sub 进去，然后算到如果 condition 可以，
哪里有 contradiction？
因为
怎么会有
example
怎么会有这样的东西？
就是
但是你不可以直接用，不是吗？因为这个情况的时候，你要 s 小于0，你才可以有这种东西存在。但是你现在是
因为我是这个我是从这里拿出来的，就 FY 搬过去吧。
不能哦，这个 fs 跟 fy 是有关系的哦，你要看你自己哦。
对呀，
你这个 fx 跟那个 fy 是有关系的哦。我就拍了答案了，
看一下，
很危险的哦。你太会抓哦，你太会抓哎。
不可以，老师。
什么不可以
这样子。
你太会抓。这样等下会很复杂哎，你就在这里看啊。
我说这个是学生，
等下很复杂哎，
学生呢？
写着啊。
我这样跟全班一起看啊。你也不要就你，那不要，就一直写了。
喂，
丢掉。
给他看不了，他考了。
啊，
这是他考。
那你可以
可以吗？老师这样子，因为这个哦，
不能，
一点点啊，
不能，不可以。
因为如果我是 prove 这样子，因为
OK， 我给你1分，因为你知道要做什么。有 B。
下面
最后一分吧，花也是。
是吧？有啊。
有。我给你1分。
还是总共4分，
没有1分吧。
越来越。
OK， 可以。
Thank you。
613。
这前面有加到很菜
613。check 一下。
因为这样多少
2分吧，6分，有。
他们要走了哈，跟我们讲。Hello. Okay, please return your test paper. Otherwise, I cannot do correction later. Need to review the. Please help to arrange the exam paper with student ID. Okay.
Thank you。
OK， 好了。OK， 不会。
就是这个，因为我有就是可以加1到这里，讲的也不可以就这个就是错嘛。反正如果是讲这个是 true 了，然后可以是 constant， 可以加1也是 constant， 为什么不会讲这是 true？
对。因为因为我们的概念是这样，我们要 check 的它在1的时候符合，然后我们假设它一个 n 符合，我们就要 prove 下一个是符合。因为这是什么意思？就是说我知道1是对的，我就能够从1推到2是对的，我不用算2是什么，但是我知道1是对，我就知道2是对。这个是可以加1的关系。OK， 可以啊。对啊。这个你怎么会 prove 呢？
老师，题目是要 prove 它如果 power set 的话是2n。
可是你 induction 哦，你怎样从
就一个一个，
你怎样一个一个哦？
从1、2、3，然后它跟着它的顺序，然后
我知道，但是你试下给我 n 等于100哦。
哦，要 prove 到完了。
要啊，你刚才讲我一个个不拿，现在我要不拿。啊呀，
这么多人改分，那个评分标准会不会变啊？
不会变，只是说我可能漏看一些东西吧。
刚好压线这边。
啊，没有，我可能是漏改一些东西吧，评分不会变的，我没有乱给分的。
就是那个30加0.7那个
啊，对，
那个浮动数不变。
什么意思？不会变，应该我会定所有的成绩会乘0.7加30，所有人。
谢谢。
OK。
不要这样说，老师。
那个 ，sorry， 没有碰到。
这个老师我不是很不明白，为什么？这里老师讲了，我不是已经证明了吗？这个为什么这个？
不是 it must be，就是它可以either n1大过 n2或者 n2大过 n1，但是我们在讨论的时候是，
它不是 strictly increasing 吗？它 x 一定要小过 x2啊。
怎么一定要？怎么你知道你一定是选一个比它小的嘞？你可能选一个比它大的嘞？你有了解吗 ？OK， 这个我可以给你示范，因为我给人家也是示范。你少了一步，只是讨论说这两个情况吧，你就少了这一步吧。有看见？第几题啊？第5题。OK。
这个老师全都是。
哦，我知道我前这个什么，就是只有这一部分是对的，这部分是错的。
这个为什么好像不可以这样子的 expand？
可以这样 expand， 可是你在做什么？没有算到东西。
有啊，这里 n 和 d 我是用这个公式啊，这个 max theorem，然后它不是讲 AT，它 congruence to A 和 M， 所以就变成。
sorry， 我好像解错了，这个应该是然后继续。继续。
哦，这样可能用公式好像不太对。
对
啊。
对啊，这个他们的
对呀，你要觉得我这个不对吗？
老师这里有报内部给你签，他前面的下面这个。
这个我知道。然后我不是很懂的是，我不是很懂的是这一步在做什么。这步我知道，你看到我步骤吗？你看到我步骤吗？你解释一下。你看。
你刚发去了。好，再见。
OK， 拜。你不是做到这里？
其实我最起码
你看你做到这里吗？可是你少了这个东西哦。然后我不知道你这个东西跑哪里去。对吗？然后我不知道你这步骤在哪里。and then， 那你就somehow得到这个东西了。所以我就不知道你这一步是什么，对吗？你这2步在哪里？这2步。OK， 你看看这2步在哪里？OK， 我这个不重要。我写出来，不是跟那个逻辑。对，但是你这个没有改，这个没有改，然后你这个改错，你就改对这个罢了，然后你这个也没有改，所以你就对一个东西吧。
这个是不知道是什么东西，
就是你用什么 law，
他有把每一步都要把
每一步都要写出来。
那这一步为什么是？这是属于美感。
哦，好，让我看看啊，我看看啊，那我看 law 了，我看看啊，还会是挤在一起的。现在 law 没有用 ，and then 你是在做什么？我看看你在干嘛？你做了什么事情？
就是这一个，
你变成这个，然后你变成这一个，然后你想干嘛？
把它背画进去。
然后呢？
然后接下来他要推这个。
哦，这样。然后这2个是因为是一样的东西。
对。
但是我是说我要用 B 吧？你怎么用 B 呢？OK， 你怎样用 B 呢？呀，我题目是说要用到 B 来证明。
有点久远。
了。不过我觉得可以给2分了，这个。 那是5分，对不对？但是你也没有解释为什么是这个问题，你是说 P implies P 哈，P implies P 哈。我给你2分。因为如果人家用 B，但是他有东西错，他们会多过3分。2分3分。你看看你几分？你是谁？9808999。对啊，算你这边够多了。要不要加你3分？3分。OK，你齐会啊。这个哈，这个用错 formula，
怎么呢？不是这样吗？你的不这样哦。不是吗？
没有，我不是，我用那个 AP 等于 P，AP
分成2个不是？
我分成，对，我分成
3跟5吗？
对。
对哦，我用这个也可以了吗？
因为这一个的话，你要 make sure 你的 M 和你的 P 是，但是我们没有这种条件在旁边。